Welcome to EE-361. This is Communication Systems, and we are currently on module or CLO number 2, and this is lecture number 12. My name is Ahmed Kamal Hassan, and I am with Faculty of Electrical Engineering. Thus far, we have basically covered 2 modules. In fact, about 2 modules. There are 4 modules in all in this course, and in the first module we talked about some introduction to communication systems that constitutes basically chapter 1 of our textbook, which is Lottie, which is by Lottie and Ding, that is Modern Digital and Analog Communication Systems, 4th edition. Right, and so in the introduction we talked about the history, the evolution of communication systems, and where we are right now, that is modern communication systems. Just to put it very precisely, the modern communication systems owe a lot to Shannon and his very fundamental paper on communication systems. That's by the name A Mathematical Theory of Communication, that was published in 1948. Communication systems actually would not be complete if we don't mention the notion of capacity, and then there is a definition by the Nyquist about capacity, and he talks about the capacity when there is what you call noiseless channel, and Shannon talks about capacity when in the presence of noise. That is, the capacity is equal to the bandwidth times log of 1 plus signal to noise ratio, SNR. Right. So moving on, in the first module itself, in chapter 2, we covered some of the aspects of a prereq, also something that we have done a review in terms of signals and systems. Herein we also talked about autocorrelation, cross-correlation, aspects of correlation with respect to radar systems. Moreover, we talked about the principle of basis and orthogonality, and how vectors play a role in terms of signals. And then we moved on from the aspects of basis on towards the basis of Fourier series, and we described, or we mentioned, that any periodic signal, if it follows 3 prior conditions, the first one being it must not have infinite maxima or minima, it should not have infinite discontinuities, and most importantly, it should be integrable. So if these 3 conditions are met, then any periodic signal can be expressed in terms of weighted sum of sinusoids. So that's a very important aspect. Like, you can represent any complex periodic signals in terms of simple weighted single tones, and then you would, if you add them up, and then you will get the same reciprocal, right? So that's where we concluded chapter 2, still in module 1, and then moving on, again in module 1 we talked about some aperiodic signals, and then we were crossed with the Fourier transform. Some of the properties were readdressed here. We moved on towards what you call distortionless transmission, and this is a very important aspect in terms of communications. Reason being that it governs a lot of principles in terms of filter design. So those areas were also touched upon. So next we moved on towards essential bandwidth. You know that any finite or any time limited signal would have an infinite bandwidth. So that's an absolute bandwidth. But then we are not really interested in absolute bandwidths. We are interested in something like 3 dB bandwidth, or some percentage of bandwidth. So that is an essential bandwidth. These are, I mean, the leakage or the spillover is basically governed by regulators. For example, in Pakistan, we have PTA that would define what are the power limits that they can tolerate beyond what you have purchased. Right. So then we moved on towards, on the similar lines, we moved on towards energy spectral density and power spectral density. Right. Now, in terms of the second module that dealt with the amplitude modulation, uh, we started by mentioning that why do we need modulation in the first place? What is the role of modulation? There are actually a lot of aspects. So one of the major one is the physical one is that the size of an antenna is inversely proportional with the frequency. So if we are talking like my voice, it is around 0 to 4 kilohertz or 100 to something like 2.5 kilohertz. So if you are going to send it as is, you would need around 15 kilometers of antenna. So it goes by like the equation C is equal to F lambda. So lambda, the wavelength, is basically directly proportional to the antenna. So if the wavelength is smaller, the size of antenna would be smaller, and hence you can have the modern telephone devices that you have right now. The antennas are actually so minimal that you don't see it in the device. So this is one of the rationales of studying modulation. Others include multi-user or multiple access or multiplexing phenomena. So you can multiplex different signals on a single channel, and or you can you can you can adjust different users on a given channel in terms of multiple access. Right. So when we're talking about modulation, we have in module 2 we are basically concerned with amplitude modulation, but later on we'll talk about angle modulation that covers frequency modulation and phase modulation. In amplitude modulation, in this module 2, we talked about DSB SC signals, that is digital double sideband suppressed carrier. We don't send the reference signal in the transmitted signal. So on the receiver side, the circuitry would be a little bit complex. You would need a local oscillator which is in sync with the transmitter, with the transmit modulator. So that is basically the downside of it. So we advance towards double sideband large carrier or amplitude modulation, in which we send the reference signal or the pilot alongside the message signal. And then on the receiver side, we usually what we do is we just use a simple circuit that includes a resistor, a diode, a capacitor to recover back our message signal on the receiver side, right? But both of them, these two are basically bandwidth inefficient, right? Inefficient in a way that if our original bandwidth of the message signal is 1B, B is the bandwidth, so the transmitted signal, or let me call it S of t, would be basically 2B. So they are bandwidth inefficient. So then we moved on towards the schemes which are bandwidth efficient. For example, let's talk about this one, SSB, which is usually 1B, like the message signal itself is 1B, and then the SSB modulated signal is also 1B, provided there is a very low DC content, right? So then it is workable. If you have significant DC content, for example in terms of TV signals, then you would need vestigial sideband. this is greater than 1B, but it is less than the transmitted signal, which is VSB of T of F. It is less than 2B. So usually it is between 1B and 2B. Yeah. So this is more often the case that we come across if we have significant DC content. Then there is another aspect, like if we can have multiple signals, we can multiplex them in terms of in phase and quadrature phase. So we can send two signals, and those two signals combined would take 2B bandwidth. So that is another scheme, right? So it depends on the application what you want to use, and this is QAM 64 QAM 256 1024 1024 is basically used in 5G right now in downlink. So they are still there in digital TV and elsewhere, right? So all of them are still there. And we concluded our last class on super heterodyne AM receiver. AM, you can also call it super heterodyne AM slash FM receiver. So this whole phenomena works for AM as well as for FM receivers. So what we do is we obtain the RF signals, and from the RF radio frequency, we use what you call a filter, a multiplier that puts the spectrum of the station of interest in a specific intermediate frequency, and then we process it and get back our original signals. In terms of the aspects that are remaining in module number 2, there are very few. We will be talking about the aspects of phase lock loop and some other carrier acquisition aspects, and then we'll move on towards module number 3.
Next, we are going to talk about phase lock loop, which is a very significant thing from the aspect of tracking uh, both frequency and phase. So, phase lock loop is used to track frequency and phase of incoming signals. It's basically a feedback system, as mentioned, used in numerous applications, including synchronous demodulation of EM signals, the thing that we have been doing in chapter 4. If we specifically mention that we have an input, and this is followed by a PLL as a system, and then we have an output. So the input in terms of synchronous demodulation of AM would be like you will be getting an AM signal, and then you will be passing it through a PLL, and at the output of PLL you will be extracting a carrier. That would be the true carrier, right? So the PLL will track the carrier of the incoming signal. Similarly, in chapter 5 we will talk about PLL in terms of FM demodulation, another significant application of PLL. Therein we would have FM at the input. It would pass through a PLL, and eventually we'll get back our message signal. And then moreover, this is used in terms of frequency synthesis, and further in terms of digital communications. We have clock synchronization and clock recovery. So in general, it's a very important phenomena, and there are a lot of circuits that accomplish the phase lock loop. The fundamental building blocks, the fundamentals of PLL or phase lock loop has basically three components. We have a voltage control oscillator, VCO, and then we have a phase detector, This is simply a multiplier. In amplitude modulation, we referred it by this symbol. So this is a phase detector, and then we have a low pass filter. Now starting with the voltage control oscillator. So as the name suggests, its input is the voltage, which I have mentioned here as V2 of t.